Thanks, Peter. Thanks for showing up and logging in online. So when I was asked to do this, I said yes. And if you're head of school, it's always there's no time in the year when there's a good time to prepare for a talk. But anyway, I've made an attempt. I hope you enjoy it. The first part will be somewhat elementary. So I'm hoping that you'll see things that you're very familiar with. And then the second half, I want to show you a little bit about the work that I've done. The work that I've done that I'll talk about is together with Zheng Chen, who recently received a PhD here at Melbourne, and together with Yori Hiki and Tomohiro Susamoto in Tokyo. So, the word universality is in the title, and in mathematical physics, in particular statistical mechanics, this is a well-known concept since the 80s in equilibrium statistical mechanics. So if you look at Wikipedia, for example, you look at critical exponents, it says that this describes the behavior of physical quantities near continuous phase transitions, so boiling of water. It is believed, though not proven, that these are universal. So there are certain behaviors that I'll explain a bit later that are universal. And that means that they do not depend on the details of the physical system, but only on some sort of general features like the dimension of the system, the range of the interaction, and sort of fairly general considerations. So that means that if you have a mathematical model, which may be idealized, you may be able to pursue certain calculations analytically and get prove a certain answer of behavior. And that may be valid then in a very large range or class of systems, like real systems or more complicated models. But you can prove it mathematically in an idealized model. The universality hypothesis then says, well, that's very broadly applicable. So some examples that are, well, so I should say that this theory in the context of equilibrium statistical mechanics is very well developed. It started in the 80s, or even earlier, I guess, but it blossomed in the 80s with renormalization theory, conformal field theory in 2 dimensions. And this is in the physics literature. So there's lots of conjectures, circumstantial evidence, numerics, quite advanced methods to compute things like critical exponents, but not prove that they actually hold. In maths, there were very few proofs. There was a bit early in this century, early in this millennium, I should say, in a development called SLE. And currently a hot topic in mathematics is Gaussian free field theory, where people try to prove things rigorously. So some examples in 2 dimensions is the Ising magnetization. So I'm hoping most of you would have sort of heard the word Ising model, even though you may not quite know what it is. It's just a very simple model that's supposed to describe magnetization. And you can prove, for example, that very close to the phase transition, where there's a point you have a finite magnetization or you have not, this magnetization vanishes as the square root of the distance of temperature to the critical temperature. And it's about this exponent here, this 1/2. That is a universal critical exponent, and it's supposed to hold for a large variety of ferromagnetic systems in real life. And some measurements have been done to prove that. But the Ising model is simple enough that you can prove this behavior. There's another model, and I think Mark is very familiar with this, percolation. And there's a similar sort of quantity you may be interested in, the probability to belong to an infinite percolation cluster, for example. So there's a critical value for that, and then you can, if your probability to belong to the infinite cluster is not the critical one, then it behaves very closely to the critical value as this quantity to the power 5/36. And this 5/36 is, of course, you can estimate that numerically to high precision, but there are quite sophisticated arguments in physics from conformal field theory or Coulomb-Gas techniques or Gaussian free field type of arguments that lead to this, but none of them are rigorous. So we have a very precise value, but it's sort of, its mathematical status is conjectural. So I'm telling you sort of a few examples of what is known for equilibrium statistical mechanics. This is not what this talk will be about. This talk will be about systems out of equilibrium. So where there's some dynamics going on. But if you hear the word universality, a lot of people will associate it with this sort of thing. So I'm going to start with a very simple dynamical system, if you like. It's the single random walker. So we have a particle in one dimension, and it can hop to the left with a rate q or to the right with a rate p. And so if x of t denotes the distance from the origin as a random variable, then the dominant behavior of that x, if you wanted to know what is the sort of likely, the expected value of x, it moves linearly in time. There's a certain drift. If p is not equal to q, the particle will on average drift either to the right if p is larger than q, or to the left if q is larger. And that's a bit boring. That's sort of easy to predict. What is more interesting is what are the fluctuations around that average, that expected value. And these are on the order t to the 1/2. And you can derive this in the following way. So you ask the question, what is the probability of finding the particle at position x after time t? And we all know this is given by a binomial distribution. It's very simple. And then you can look at it asymptotically when time is large. And you very quickly deduce that the dominant contribution is linear in time, and the fluctuations are of order square root in t.
So is time discrete here or continuous?
Well, I sort of take a scaling limit, so it just either if it, it's sort of in the, basically when you go from a binomial distribution, and I'll do that on the next slide, to the Gaussian distribution, the normal distribution, you take a scaling limit where you.
Sure, but when you're saying it's binomial, it makes me think it's discrete.
Yeah.
When you're saying rates and not saying that q equals 1.
So for me, discrete and continuous is not really that big a difference from the point of view I want to take. So I start with a discrete model, but ultimately I'll take a sort of scaling limit where space becomes continuous in time. So not only can you can sort of estimate the order of magnitude of your fluctuations, which are in the order of square root t. You can say more. You can be much more precise of the, well, you can even give a formula for a probability, right? So what is the cumulative probability that the scaled fluctuations, so that is this quantity here, we take the random variable, the distance to the origin, subtract the boring linear part, divide by the right order of magnitude in t, square root of t, and then you have to adjust with some numerical constants, and you ask what is the probability for large times that this quantity is less than a certain number, s, and that is given by an integrated Gaussian, or integrated normal distribution. And in this context, we can talk about universality in the sense that this normal distribution pops up at a lot of places, right? We know. So we like to say that this functional form is universal in the sense that it's very broadly applicable to a large number of problems, not just a single random walker, but many other problems. So as long as you sort of have the right numbers, sigma and v, which can be model dependent or dependent on the system that you look at, everything else is universal.
The integral from minus infinity to s?
In this case, it's as if s is positive, you can go from the origin. Or maybe I should have put absolute values around this. Again, this talk was prepared in with little time. Okay, so this is a simple, of course, we're all familiar, well, at least we've sort of seen this in some form or another. It's a very simple system, and you can pursue the mathematical analysis into great detail. And one of the reasons for that is that it's a non-interacting model. It's just a one particle moving on a line, and there are no other particles or no interactions. So it gets a bit more involved and maybe more interesting if you have interacting systems. But then also it's mathematically more difficult, particularly to prove. So the things I mentioned on the first slide were examples of interacting systems, and then with physics argument you can still say quite a bit, but the mathematics is much harder. So the aim will be, can we say anything about interacting systems in a mathematical sense? We want to prove certain things. And here's one other toy model that I've played with quite a bit. It's called the simple asymmetric distribution process, or ACEP, if you commute these two words. So this is a very well-known stochastic particle model, but now instead of having a single particle, we have many particles, and they interact through exclusion. So they can, like the random walker, they can hop to the left or to the right with certain rates, but particles cannot occupy the same site. So there is an exclusion interaction, if you like, that this particle is not allowed to hop to the left because there's already a particle there. And this interaction, so this is just one toy model with a particular type of interaction, but that sort of interaction causes non-trivial collective phenomena. Told I should use the mouse. So non-trivial collective phenomena. So, for example, and we'll go into more detail later in the talk, if you wanted to know the particle current, let's call it J of t, defined as the net number of particle jumps across the origin after time t. So say the origin was here, and you just let the system evolve under its rules, and you just keep counting the net number of particles across your origin, and you call that JT. Then
is that in either direction, Jan?
Yeah, the net number. So plus if you go to the right, minus if you go to the left.
All right.
Again, that if P is not equal to Q, if the rates are different, there will be a drift, right? So if P is larger than Q, you would expect more particles to move to the right than particles move to the left. So there'll be a net drift, which you call V. So the leading term of J of t will be linear in time again, just as before, but now the fluctuations around this expected behavior are t to the 1/3 and not t to the 1/2. So that is an effect of these interactions that you have in the system.
Is there some constraint on how you have to start the system?
Yeah, so you can start a system in many ways. You can start, say, by filling the negative line, the negative half space, or you can start with alternating particles. There are different ways. That doesn't really affect this 1/3. It will affect the distribution function that we'll look at next, but not particularly this 1/3. So that's already sort of a manifestation of the universality, I guess, of the 1/3, right? The 1/3 we see in lots of places, and I'll show you an example later on. But we can actually do more for this particular model. Again, this is an idealized model, a sort of a model which has very special properties, and because of that, you can push the analysis much further. You can give the distribution of these fluctuations And sort of this was a quite exciting results in also early millennium. And this distribution is no longer given by a normal distribution, but by a Tracy-Widom distribution, which appears in random matrix theory. So what you have to do is take this particle current, J of t, subtract the boring linear part, then you have to scale it with the t to the 1/3, so that you look at, zoom in on the right scale, and then up to these constants, sigma and v, which will depend specifically on this model. You can ask, what is the probability that these fluctuations are less than a certain number s, as time is very large? And that is known, and this is a proof mathematically, to be given by the GOE distribution from random matrix theory. So this is the unitary ensemble in random matrix theory. And it describes the distribution of eigenvalues of random matrices.
The G is Gaussian.
The G is Gaussian. Yeah.
Right.
Well, so we'll see that later on as well. That's some input which is Gaussian, and then the output is not Gaussian. And that has to do with these interactions. Anyway, so this is sort of my introductory slides to sort of set the scene. Are there any questions at this point? Okay. So one more slide, I guess. So there's, if you can plot the Gaussian and compare it to the Tracy-Widom distribution. I've done that here. So on the earlier slide, I had the cumulative distribution. So these are the distributions themselves. The Gaussian in orange and the random matrix theory in blue. So there's some slight differences. The random matrix theory, the GOE distribution is not symmetric. So there is some differences between the right hand side and left hand side. And there is actually quite an explicit form for this distribution. Not as explicit, of course, as a Gaussian, but almost. So it has this form. This, GOE, Tracy-Widom distribution, can be written as the exponential of this integral. And inside the integral, there's this function u, and u is the solution of a Paine-Levé 2 equation, which is given here, subject to the asymptotic boundary condition that u approaches the Airy function as x goes to infinity. Right? So this uniquely determines u, and then you plug it in here. So this is as explicit as you can get it. But from this, you can very quickly draw this picture. There are other expressions for f, but they ultimately can be related to this form. Okay. So maybe it's already clear that from this expression here, and this somewhat implicit form of the Tracy-Widom distribution and the appearance of Paine-Levé, you may have to do some work mathematically to get there. And I will try and sketch some of the details, and some of the slides are, well, we'll get there. All right. The sort of general behavior of models that behave in this way, we call a universality class of models, of systems. And the ones that behave in this way are called the KPZ universality class. And I want to explain the origin of that. So in the 80s, people looked at growth models like this. So you have a one-dimensional substrate, and you think of it being present in some gas chamber or rarefied gas that where the atoms can in some way adsorb to the surface, so that the surface profile grows. And you'd like to describe the height profile of this surface, right? So the model that was written down by physicists Kardar-Parisi-Zhang, hence KPZ, in 1986 was one of stochastic growth normal to the surface. And the basic object is this random height function. Let's call it h. And the assumptions were that this h solves a nonlinear stochastic partial differential equation called, since then, the KPZ equation of this form. And it says that the rate of change of the height function h is equal to a diffusive term, so that's a second derivative in space, a nonlinear term, which is this one here, which is like the first derivative of h squared, and that arises with the assumption that the growth to the surface is in the normal direction. If you just go through the derivation, that will give rise to this term here. And then you add to that Gaussian random noise. And so this is sort of an input that is Gaussian, which we also see in the random matrix theory, where your entries are distributed using Gaussian. Here, it enters in this way. So the assumption is that that growth, that one plus one dimensional growth, is correctly described by an equation of this form. So the claim is diffusion, that first term, plus nonlinearity, the second term, plus Gaussian white noise in space-time correctly describes 1 plus 1D surface growth. And that was sort of numerically investigated for a particular model in 1986. But it was realized in liquid crystal growth in the Takeuchi lab in Tokyo. So Takeuchi is a colleague of Sasamoto. They're in the same institute, and I visited them a few times, and one time in 2017. And here they are. So this is Takeuchi, and this is his sort of setup. And he can sort of measure, and I have a movie of that I want to show. So this is, you're looking at a computer image of a liquid crystal where I think it's a nematic crystal, and the molecules have different orientations. And then when you shine light on it, you can well, you know, if it's light, then it's a phase in one orientation. If it's darker, it's in a different orientation. And so what he does, he prepares a sample of this liquid crystal in somewhat critical state. And if you then hit it with light or some impurity, you can make a droplet grow. It's like a coffee stain grow or a wine stain. And so here's what happens. So you see it grow. And you see it grows linearly in time. The overall droplet just grows. And that's a little bit dull, but it's not entirely uniform. There's some fluctuations at the edge, right? And you'd like to describe, I guess, what's the size of these fluctuations? And Takeuchi measured that these are exactly at the order of t to the 1/3, and so confirming sort of this sort of behavior here. So these fluctuations of that boundary of the droplet are not Gaussian; they are t to the 1/3, and that sort of means that the assumptions that were made to write down this equation were correct, because this equation correctly reproduces that outcome, that the fluctuations grow with t to the 1/3 and not the square root of t. There's a lot of activity about the KPZ equation. In 2014, Hira got the Fields Medal for mathematical work on this equation, because, you know, if you look at this, there's a random function here, or random distribution, and you also take derivatives of h. So those two things don't go together in a natural way. It's not obvious that h actually is a differentiable function or that this equation is well posed, because you're just throwing in different objects. But Gier showed that you can actually make sense of this, and this is actually a well posed type of equation. So lots of activities in physics and in mathematics. Okay, so in summary, what are the main features? Well, you have some observable, whether it's a height function or something else that may have some rather dull behavior, but then the fluctuations are not square root. They are not Gaussian, they are something else. Yeah. Another way of formulating the KPZ equation is through the stochastic heat equation. So if you take a transformation, you write h as the logarithm of a function z, then z satisfies this equation here. And without the last term, this is the heat equation, and then you add this random white noise, and then this is called the stochastic heat equation. And sort of, I think it's in this form that Gier showed that this is the right way to formulate your problem. Okay, so I'm going to show you more detail now. So we're going to focus on this function z. So z is related to the object that we're interested in. And there is an explicit expression for the expectation of something of this form, e to the negative zeta z. So, and the statement is that you can, if I take the expectation on the distribution of the stochastic heat equation of this object here, where time grows large, and you look at it at the origin, then this can be written as a Fredholm determinant with this airy kernel in here. So it's just a formula that you can derive, and from this you can then do further analysis and get down to this expression here. That so from this you can extract that the probability that the height function scales, that the fluctuations, the height function scale on the order of t to the 1/3 with a distribution given by the random matrix distribution GUE. So it's quite an effort to get to this stage. It's quite an effort, and I'll show some of the detail. It's quite an effort to get to this stage. Then it's another effort to get from here to there. But these two are sort of equivalent. So nowadays it's very well understood. Once you get to this point, it's well understood how to get here. What I'll be showing you today is sort of how, sketched is how to get to this point. And you have to just believe me that from there, it's not obvious at all, that from there you can, this sort of airy kernel property is the key feature to get to here. Okay, so we saw that these t to the 1/3 fluctuations occur in liquid crystals, in other growth models, and also in this model system, the asymmetric exclusion process. So I want to now go into a little bit of detail on how it appears. So this is your model. You have, you define a model with particles on the infinite line, and they can hop to the left and to the right, except when there's a particle next to each other, then the exclusion rule tells you that this particle cannot jump to the right because there's already a particle there. And we were interested in a quantity that I called J in an earlier slide. I call it N here, that the number of particles to have crossed a given site Y after time T. Well, J was the net current. This is just the number of particles. Now you have to sort of look at a slightly different object to make it mathematically easy to do calculations. So we actually don't want the expectation of n, but rather the expectation of q, which is the tau to the power n, where tau is the ratio of the hopping rates. So it turns out that the expectation of this object is easier to calculate mathematically than n directly. But once you have this, you can, of course, deduce the desired properties of n itself. Actually, it's not even q that you're interested in. Somehow you need to take the space derivative of q. So you really want to know n, you write it as q as tau to the n, and then you take the difference of q at two different at neighboring points in space. I call that q tilde. Okay, so it turns out that now if you wanted to compute the expectation values of q tilde, or the moments of a product of these q tilde at various points, so you count the number of particles at different points in space, x1 up to xk, that this expectation value, when you average over the configurations of the ACEP, can be written using this multiple contour integral. So you have to take k integrals here, the number of points that you're looking at, over some sort of expression that if you see this for the first time, it probably looks horrible. But if you are used to this, then this is a very nice expression. The first thing that's really nice about it is that it's factorized. You have to integrate over k variables called zj. But this part of the integrand is completely factorized in those zj's, right? So there's just the product j equals 1 to k of these factors. This lambda is a known and very simple rational function. The thing that's not factorized is over here, but this is quite simple as well. This is the product of the differences of zi minus zj, which is known as a van der Waals determinant. So it has nice determinantal properties, and in the numerator is like a deformation of it. But tau again is the ratio of the hopping rates. And so you have to evaluate these contour integrals where you integrate around the origin, right? So you have to compute the residue basically of this thing around the origin for all the k variables. So I'm not going to say much on how to derive it for this model, except to say that the expectation value of these moments of the exclusion process are somehow related to the what is called the quantum Bose gas with delta function interaction. So there's some other model in physics that allows you to write down this expectation value in a very explicit form. So from this, you need to now calculate this. When t grows very large, t is up here in the exponent. So we want to know asymptotic times, very large t. And quite often we're also interested in having k large. So you have to take this product large, and the number of integrals you have to perform grows asymptotically. So you can see that's not, from here, it's not entirely obvious how you should do that, but that can be done. And then because of this explicit form, and because of some advanced complex analysis, it's one way of arriving at these sort of statements. And we'll go into deeper into that yet. How am I doing for time?
You've got about 20 minutes.
Okay. So the summary of what I've told you so far is there's a few ingredients. First of all, we have a stochastic lattice model, which is like an idealized model of some phenomenon we're interested in. And the models I showed you have some nice mathematical property, which we call integrability, which means you can actually pursue calculations to quite some detail and arrive at these integral expressions. So you may still think, well, you know, I didn't really like that integral that you wrote there, but the fact that you can write it is already quite something. Most of the time, people just numerically simulate models and can't really go beyond that. I also want to point out that there's related work by Sasha Gavali and Michael Wheeler here at the University of Melbourne on integrable stochastic lattice models related to multivariable polynomials and special functions. But we also saw there was some observable expressed in terms of a k-fold complex contour integral, and then I sort of said that you need to compute the asymptotic behavior of that integral when k is very large, meaning you have to take more and more integrals. And that is not obvious how to do, but there is a trick involved, which I'll point out, and you need to consider things called Fredholm determinants. And then that asymptotics you can do. This is well known from people doing random matrix theory. Once you have it in that form, you can do a saddle point analysis and get to the asymptotic form. So this sort of a body of work that was done over the past, almost 2020, so the past 20 years. So this was started in 2001, and there's been a lot of progress. But what hasn't been done is looking at models where you may have two different types of species of atoms, right? So we saw we had a model with many particles, but they were all the same. You think of that there may be models where there are, and we will look at this, where there are two different types, two different species of particles, or more than two. And that's of interest when you want to consider, for example, fluid mixtures, and you want to understand the fluctuations in there. The reason why there hasn't been a lot of progress there is because this leads to something called dynamic poles in the integrals, which are very hard to deal with from a technical perspective. So that's been quite a hurdle, and I'll try and point that out a little bit. But in the end, we find that we have a model for which you can do all that. And we find that finally the fluctuations in that model are a combination of Gaussian modes and GOE modes. So there's some mix between normal modes and KPZ normal modes. So the rest of the talk until the very end is going to be quite technical about some of these things. But I'll try and, well, okay. So here's the model. So as I said, there's going to be two families of particles. And in the picture, they are purple and green. And purple is also black here. So we have particles that move to the right with a certain rate, p. Right? So if the, I mean, this is a space-time diagram. Space is horizontal and time is vertical. So if your particles are at certain positions at say time 0, then they start drifting to the right according to this rule. Right? So you just pick uniformly at random a site, and if there's a particle there, it hops with a rate p. The same for the green particles, but the green particles move to the left. So if you have an empty site in front of a green or white particle, then the particle can move to the left. So if there's no, well, maybe look here. If there are green particles without purple particles around, they just move to the left, stochastically, with this rule. But of course, they interact, and if you have a purple particle in front of a green particle, they can interchange, with rate 1, but they cannot change back. They can only, like, black-white can interchange into white-black, but you can't go back. So this is a typical snapshot of an evolution of the model from a certain initial condition to a certain final condition. And once the two families have completely exchanged, as what happened here, they'll sort of start to keep doing their own thing and no longer interact. But the interesting bit now is, can we describe the middle region where you have a mix of particles? So what are the fluctuations there? You know, what are the typical, what's the typical behavior inside? Like the typical currents. So you can do something similar to KPZ, some physics theory. So this is like a heuristic theory. And it's a generalization of this KPZ phenomenon to multi-species models, or also to higher dimensions. And the ingredients are, again, that you want to, well, what are the ingredients? You start with the continuity equation, which always holds. So if U is the density and J is the current, then the continuity equation is just basically particle conservation. It's that the time derivative of the density plus the space derivative of the current should equal 0. So that's a very general property of all these models. What you need to know, though, is how to express the current in terms of the density. And you can do that using a sort of mean field assumption. So it's basically incorrect, but somehow it works for the physics. And in this case, there are, and I don't really want to explain details of it, but just to show you that there are explicit expressions of the current of these purple particles or black particles in terms of the densities of the black particles or plus particles, as well as those of the other type of particles, the minus particles. So rho are the densities, and then the current can be expressed in terms of those sort of mean field type densities. And this is analogous to the nonlinear term in the KPZ equation, right? You see here that this is rho plus squared appears. So if you view this as an equation for the densities rho plus and rho minus, so U is expressed as rho plus rho minus, then there will be nonlinear terms here. And then the claim is for this nonlinear fluctuating hydrodynamics, if you have such an equation, continuity equation, which can be nonlinear, you have to add diffusion and noise, as we did in the KPZ equation, and that should correctly describe, from a physics perspective, the fluctuations in these particle models. And then you can sort of do some physics and find that this theory predicts an expression for the total crossing probability that is a product of the Tracy-Widom random matrix distribution times that of a Gaussian distribution. And the parameters S plus and S minus that appear here are some scaled versions of eigenmodes of this two-dimensional system. So the aim then of our work was to prove this rigorously. So this is sort of physics prediction. Can we prove this this behavior in a rigorous way?
So Jan, this appeared in some physics paper as, I guess, conjecture from our point of view.
Yeah. Yeah. So I just want to sketch a few main tools that we use. So first of all, we compute the green function of the model. So that is a solution of the master equation. So you know, this is a simple, we're looking at a simple Markov chain. You can think of G as the probability to find a certain configuration of particles at time t, and the rate of change of that. The rate of change of that is given by some linear relations. So there's some matrix M, which is the transition matrix that describes the rules of the game, and then that probability is just a solution of this linear equation, subject to a certain initial condition, namely that at time 0, all the particles are at their original sites, which you can specify. So the x0 and y0 are just the initial configuration that you specify. So normally it's very complicated to write down a solution of this equation unless your model has very special properties. And in this case it has. So we can solve that Markov master equation of the Markov chain in an explicit form by using a technique called beta ansatz. So this is something I use a lot in my work for other things. Well, there's some details there that I'll skip. I just want to show you the sort of explicit form. And again, this looks horrible if you see it for the first time, but if you're used to this, it's not that bad. So let's first look at the integrals. So if I have n plus particles and m minus particles, I apparently need to take n integrals over variables zj and m integrals over variables w. There's this e to the lambda t, where lambda are the eigenvalues of the transition matrix. And then there are these two determinants. So the first determinant is the blue one. It only contains z variables. And it basically encodes that the plus particles cannot occupy the same site. There's an exclusion principle there, like we had in the ACEMS. And because this is a determinant, if two of the x's are the same, the determinant will vanish. So this sort of incorporates the fact that particles cannot occupy the same site. We need another determinant for the other family of particles, the minus particles, the ones that drift to the left. They also satisfy exclusion. And we need a determinant for that. And this is somehow the right form. Then there is this interaction between the two families. So they can interchange, right? But they can only interchange one way. For every interchange, we need a factor that looks like this. So the details of this formula are such that they solve the equation, the master equation. So I don't want you to really focus on the detail here. I'm just trying to explain the essence of the formula. Because it's an interaction of the two families, it will include both the z variable and the double variable, right? They interact, so they appear together in this expression. They are not separated or factorized like here, where I have a determinant with only z variables and then another determinant with only w variables, right? So these two expressions by themselves don't interact, they're a product, but once you have this, there is an interaction. And this lambda is known explicitly. As I said, it's quite a simple function. It's of this form. So I claim, and we prove this, this is the green function for my two-species model where particles can cross. It solves the master equation, the Markov chain master equation, and it solves the initial condition at time equals 0. Okay, so that's just, this is what it is. Now, we wanted to know, for example, if we go back to this picture, what is the probability that after time t, the two families, given a certain initial condition, so say this initial condition here, what is the probability that after time t, they have fully crossed? Right? So that after certain time t, we are in this state where all the white particles are to the left of all the black particles. So once you have the green function, you can compute that probability by summing over all the final coordinates, right? So if this is your initial condition, then the Green's function will tell you the probability that the two families have crossed if you order the final coordinates in the right way and sum over all their values. So it's some you have to take, and then something nice happens, because if you compute that sum, the integrand in these contour expressions completely factorizes. So previously in the Green's function we had determinants. Once I perform these sums, the determinants have gone and the whole thing completely factorizes, except for these van der Waals determinants here and the one in W. Everything else is factorized. It still looks complicated, but the fact that it's factorized makes it easy. Now we just have to calculate this when n, m, and t grow very large.
Sorry, yeah, I wouldn't say factorized, but you still have the z in the red thing in the bottom right. Don't you have the z's and the w's interacting there?
Yeah. So that's why it's in red. So that's the it. Well, it's sort of factorized in a certain way, but not fully. Yeah. So we'll get to that. So you need to take the contours around the origin, and then compute this when n is large, m is large, and t is very large. Right. So it's still problematic in this form. It's also problematic because this e to the lambda term produces an essential singularity at the origin, because this lambda function looked like this. So you have 1 over z and 1 over w inside the exponent, where t is very large, and we had to compute residues around the origin. So the first thing we need to do is redraw the contours around all the other poles except the origin, because otherwise we can't really compute this integral in a good form. So you do that, but then you quickly realize that only the simple poles at w is 1 give a non-zero contribution. So it looked complicated, but fortunately it simplifies. So then you can, because these are all simple poles, you can evaluate it, and then you end up with an expression where you only have integration over one variable, one family of variables. Right. So there's some change of variables. You can get it to a form that is known in the literature for the single species star set. And that is part of that body of work of the past 20 years that I sort of sketched in the first half of the talk. And we're basically done. I don't really want to go into the details, but from here, you can go to the Fredholm determinant expression, and from there you can go to the Tracy-Widom type formula. Clearly, there's still a lot of work to be done, but you know, that's in the literature. So I started with here. I started with this very special initial conditions where the particles were closely packed. It gets a little bit more interesting when you start with a Bernoulli random initial condition for the black particles, when you keep the white particles still closely packed. Your formulas change a little bit. There's this, so this distribution is with parameter rho, and then your formula is adjusted with this sort of factor here, which produces a pole at 1 over rho.
So sorry, what is the actual distribution of the black particles? So you're just going distance m or n to the left?
I have finitely many particles, and I just at every site you drop one with probability rho
Until you run out.
until you run out. So the n particles.
Yeah. And okay, so what's random is not the number, but where you're putting them.
Yeah. Yeah, and now we need to analyze this where the particle numbers are very large. we want to grow to sort of finite densities of particles. And in such a way that the number of black particles is less than the number of white particles. Why? We're interested in this sort of middle region where the particles interact around the origin. Because the black particles are distributed further out from the origin than the white particles, because these are closely packed, I need to have less black particles than white particles if they all sort of arrive at the same time around the origin, if I want to measure non-trivial effects. So that's why you need to analyze this when n is less than m, and that turns out to be highly non-trivial. So Peter is standing, meaning I need to wrap up. I've shown you enough sort of complex formulas to sort of give you a flavor of what the complexity is here, but we managed to get through that. And in the end, you can we arrive in a rigorous way at this airy distribution for one of the eigenmodes of this system. Final slide is that from the formulas that I very quickly flashed in front of you, we can derive that the probability that the two families cross in a certain scaling limit given by these variables, and one of them, the scale of the fluctuations around these variables is on the order t to the 1/3, and the fluctuations in the other mode are Gaussian, they are square root of t. So these are certain scaling variables, and in that scaling limit, the probability of total crossing factorizes as a GOE, random matrix Tracy-Widom distribution, and a Gaussian distribution in the other eigenmode. And then, so if you plot it, it looks like this. And this is our theorem, so it's no longer heuristics, or you can check it numerically, of course, but once it's a theorem, you don't have to check it numerically anymore. Okay, so that's the conclusion. So we had the first proof, and we're quite proud of this, and it got accepted in FIS Rev Letters, and it was highlighted as a publication, so we're pleased with that. First proof of nonlinear fluctuating hydrodynamics for a two-component mixture. I want to stress that we used integrability here, some special properties of these models, and we found a mix of Gaussian KPZ modes. And I didn't really get to the point how we deal with dynamic poles in the integrand, but that's the main technical hurdle that we solved to be able to prove this. But the next step would be, of course, can we generalize this now to multi-component mixtures? And that's sort of work for the future. Thank you.